Hello student, myself Dinesh Prabhakar. Welcome to Process, Dynamic and Control lecture series. In my previous lecture, we discussed about the rate of reaction and factor affecting the rate of reaction. So we know there are different type of factors that affect the rate of reaction like temperature, size. So now in this lecture, we discuss about the temperature control, and then after we discuss about the reactor time constant. So in this lecture we discuss about the temperature control and reactor time constant. So now we start temperature control. So first of all, one question come in our mind: what is the purpose of temperature control? That means why we require temperature control in a reactor? So the answer is the purpose of this control system is to ensure the chemical solution inside the reactor vessel is maintained at a constant temperature. So this is the main aim or the purpose of this control. So the question is, why we require temperature control in a reactor or in the industry? Why we require temperature control for the reactor? So the answer is to ensure the chemical solution inside the reactor vessel is maintained at constant temperature. So this is the aim of this controlling system. So this is the simple diagram of temperature control system. So here you can see in the rectangular, this is the reactor, and surrounding of this reactor there is one jacket, and TT is indicated temperature transmitter. That means this is one sensor that sends the temperature inside the vessel and is sent to the temperature controller. And according to temperature sensing, the temperature is controlled by the throttling valve. You can see this is the heat transfer supply is run in the surrounding of the jacket, and by using this heat transfer supply, we control the temperature inside this vessel. A simple temperature control scheme is shown in figure. The steam heat jacket envelope the reactor vessels, transferring the heat from the steam into the chemical solution inside. The control system maintains a constant temperature by measuring the temperature of reactor vessel and throttling steam flow and steam flow to add more or less heat as needed. That means here, this is the temperature controller. You can see is maintain the temperature inside this closed vessel or the inside this reactor by throttling. That means opening or closing the valve. So if we require more heat, then at that time it open more valve. And if we require less heat or the less temperature, at that time is close the valve. So by opening and closing, or we can say the throttling the valve, we can maintain the temperature inside this vessel constant. So this is a simple method of controlling the temperature. Now we discuss another method. So before we discussing the another method, there are some limitation of the previous method. So which are that limitation? So first one limitation is this method of cooling is undesirable because the coolant temperature is not uniform. this can cause cold spot near the inlet and hot spot near the outlet. So this is the main limitation or disadvantage of previous method. So it creates a cold spot and hot spot near the inlet and outlet. Now second one limitation of this method is, another limitation of this configuration is the variable residence time of the cooling water within the jacket as the flow rate changes. So this is the second one limitation of this method. And now last one limitation is, in addition, when the water flow is low, the Reynolds number will drop off, and with it the heat transfer efficiency will also diminish. So that means the efficiency is also affected by this controlling system. So when the water flow is low, the Reynolds number will drop off, and with it the heat transfer efficiency will also diminish. So these are the limitations of the temperature control method that we discussed in the previous slide. Now we discuss about the next one method of temperature control. So for all above reason, that means in the previous slide, the recirculate cooling water configuration shown in figure is more desirable because it guarantees a constant and high rate of water circulation. So this is the main advantage of this method. The name of this method is recirculate cooling water. So here we get the constant and high rate of water circulation. So here you can see the temperature transmitter TT is transmit the temperature to the temperature controller, and it also the temperature is controlled by using the supply of the heat transfer. But here we use the pump. So this is the by using pump we can maintain a constant temperature inside this cooling system. This keeps the jacket dead time constant, the heat transfer coefficient high, and the jacket temperature uniform, thereby eliminating cold and hot spot. So this is the advantage over the previous controlling method of the temperature. The fluid velocity in the reactor jacket is maintained high enough to produce satisfactory film coefficient for heat transfer. So these are the advantages of the recirculated cooling water system. So this is the second one method of controlling of the temperature. Now we discuss about the reactor time constant. The amount of heat generated by an exothermic reactor increase as reaction temperature rise. Of course, we know there are two types of reaction, exothermic and endothermic. But we know in the exothermic reaction, the amount of heat is generated is increased as the reaction temperature is increased. If the reactor is operated without a temperature controller, or we can say in an open loop, an increase in the reaction temperature will also increase heat removal because of the increase in the delta T between the process and coolant temperature. If increase in the reaction temperature result in a greater increase in a heat generation, then in a heat removal, the process is said to display positive feedback. As such, it is considered to be unstable in open loop. The positive feedback of the open loop process can be compensate for by the negative feedback of a reactor temperature controller, which will increase the heat removal rate as the temperature rises. The addition of such feedback control can stabilize an open unstable process only if the control loop is fast and does not contain too much dead time. That means by adding additional control, that means we add the feedback control system that increase the efficiency of system. That means unstable process if the control loop is fast and does not contain too much dead time. Now, according to Shinsky, suggests that if dead time can be kept under 35% of thermal time constant of the reactor, the process can be stabilized. Whereas if it approaches 100%, the reactor will not be controllable. So this is the assumption according to the Shinsky. He said, if we keep the dead time under 35% of thermal time constant of the reactor, the process can be stabilized. But if it approaches 100%, the reactor will not be controllable. The real reactor has several legs and delays, including those of measurement and heat removal. The equation for calculating the thermal, reactor, wall, coolant and thermal pump time delay are listed below. Typical value of this time constant are tau 1 is indicated thermal time constant and its typical value is range between 30 to 60 minutes. Tau 2 indicate the reactor wall time constant and its typical value is between 0.5 to 1 minute. Tau 3 indicate the coolant time constant and its value is between 2 to 5 minutes. And last one is tau 4. This indicates the thermal bulb time constant and its typical value is between 0.1 to 0.5 minutes. And we can be minimized by the use of the bare bulbs. Now, we discuss about the thermal time constant. So, we can find out the thermal time constant by using this equation. Tau 1 is equals to W1 C1 K1 into A. And we can also write this equation as W1 C1 upon Q into T minus T1. And here, the W1 is indicate the weight of reactant, C1 indicate the specific heat of reactant, K1 indicate the heat transfer coefficient, and A indicate the heat transfer area, and Q indicate the rate of heat evolution. So this is the equation to find out the thermal time constant. Now we discuss the reactor wall time constant. So reactor wall time constant we can find out by using this equation. So the tau 2 is equals to W2 C2 I K2 into I, and we can write this equation as W2 C2 upon Q into T1 minus T2. So here W2 indicate the weight of wall, C2 indicate the specific heat of wall, K2 indicate the thermal conductivity, and T1 indicate the wall temperature, and T2 indicate the outside wall temperature, and I indicate the wall thickness. Now, coolant time constant. So coolant time constant can be find out by using this equation. That means coolant time constant tau 3 is equals to W3C upon K3 into A. So we can write this equation as W3C upon Q T2 minus TC. here the W3 indicate the weight of jacket content, K3 indicate the heat transfer coefficient, TC indicate the average coolant temperature, C indicate the specific heat of coolant, and last one is the thermal bulk time constant. And thermal bulk time constant can be calculated by using this equation: tau4 is equals to W4 C4 K1 A4. So here A4 indicate the surface area of bulk, C4 indicate the specific heat of bulk, and W4 indicate the weight of bulk. So this is the reactor time constant. So in this lecture we discuss about the temperature control and then we discuss about the reactor time constant. Thank you.